There's a machine sitting on top of a mountain in Chile that just changed everything we thought we knew about the universe. Not metaphorically, not eventually. Right now, in this moment, as you are reading these words, that machine is staring into the deepest corners of the cosmos and sending back data so overwhelming, so relentless, so incomprehensibly vast that no human being alive could process it alone. Every single night, it generates around 20 terabytes of data. Every single night. And it has only just begun. But here's the part that nobody is talking about loudly enough, the thing that should stop you cold. We have spent decades searching the sky with the best telescopes humanity has ever built, and we thought we had a reasonable picture of what was out there. We cataloged the stars, we mapped the galaxies, we tracked the asteroids, we told ourselves we understood the neighborhoods. And then the Vera Rubin Observatory switched on its camera, the largest digital camera ever constructed in the history of human civilization, and in the very thousand objects we had never seen before. Objects that were hiding in plain sight right here in our own solar system. Think about what that means. We didn't know they were there. We had no idea. And that was before the real survey even started. This is not a story about a telescope. This is a story about how wrong we have been, and how terrifying that wrongness actually is once you understand the full picture. Let's go back to the beginning, because the beginning of this story is not where most people think it is. The Vera Rubin Observatory, officially known as the NSF-DOE Vera C. Rubin Observatory, has been more than 2 decades in the making. It sits perched at the summit of Cerro Pachón in Chile, where dry air and dark skies provide one of the world's best observing locations. The mountain stands at 2,682 meters above sea level, far above the atmospheric haze and light pollution that blinds every observatory built at lower altitudes. It took 25 years of construction, commissioning, engineering, and scientific validation to bring this machine to operational status. 25 years of work by thousands of scientists, engineers, and researchers across multiple nations and institutions. And the reason they built it, the real reason, the driving scientific question behind the entire project, is one of the most unsettling facts in all of modern science. We don't know what most of the universe is made of. The familiar objects around us that are made of matter and energy, people, planets, stars, account for only about 5% of what there is. 5%. Everything you have ever seen, touched, measured, or imagined represents just 1/20th of the actual content of the cosmos. The other 95% is something else entirely. Scientists call it dark matter and dark energy, which are not so much names as they are elegant labels for profound ignorance. We know these things exist because of what they do to everything around them. We can see their gravitational fingerprints on galaxies, on light, on the large-scale structure of the universe itself. But what they actually are, what they are made of, how they work at a fundamental level, that remains one of the deepest unsolved mysteries in all of physics. And the Vera Rubin Observatory was built, specifically and deliberately, to crack that mystery open. But here's where it gets more interesting than anyone expected. Because while the scientists were setting up their instruments and calibrating their systems and preparing to begin the grand 10-year mission, the telescope was already making discoveries. Even before the main survey officially began, even in its earliest test phases, Rubin was already rewriting the inventory of our solar system in ways that should make every person on this planet pay very close attention. In June 2025, Rubin released a set of images taken during its first light, including photographs of 1,500 new asteroids. That was just the opening act, a preview of what was coming. By the time the pre-survey optimization phase had concluded, the numbers had grown staggering. Scientists have discovered over 11,000 new asteroids, with the data confirmed by the International Astronomical Union's Minor Planet Center, making this the largest single batch of asteroid discoveries submitted in the past year. The discoveries were made using data from Rubin's early optimization surveys and offer a powerful preview of the observatory's transformative impact on solar system science. The submission to the Minor Planet Center comprised approximately 1 million individual observations, taken over just a month and a half of looking. Read that again. 1 million observations, 11,000 new asteroids in a month and a half, before the actual survey had even started. In just 6 weeks of optimization phase observing, the telescope discovered more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects beyond Neptune's orbit. The near-Earth objects are the ones that demand your attention. Near-Earth objects are asteroids and comets whose orbits bring them into the vicinity of our planet. They are the category of solar system objects that planetary defense scientists monitor most carefully, because they are the ones with the potential to cause an extinction-level event if they are large enough, and if their trajectory intersects with ours. And Rubin found 33 previously unknown near-Earth objects, 33 rocks in space whose existence and orbits were completely unknown to science until this telescope looked, and it found them before it had even properly started working. But even that is not the most alarming discovery that emerged from Rubin's first months of operation. Something else happened, something that shook planetary scientists in a very specific and visceral way. In January 2026, researchers announced that 19 of those asteroids were spinning especially rapidly. The quickest of these superfast rotators, an asteroid with a diameter almost twice the height of the Empire State Building, called 2025 MN45, completes a revolution every 1.88 minutes. 1.88 minutes. Think about what that means for a moment. An object at nearly twice the height of the Empire State Building, spinning so fast that it completes a full rotation in less time than it takes to make a cup of coffee. This is not normal. This is not supposed to be possible in the conventional understanding of asteroid physics. Most asteroids are believed to be what scientists call rubble pile. Asteroids, which means they are made of many, many small pieces of rock and debris that coalesced under gravity during solar, system formation, or subsequent collisions. A rubble pile spinning at that speed should fly apart. The centrifugal force generated by a rotation every 1.88 minutes should exceed the gravitational force holding the pieces together, and the whole thing should disintegrate into a cloud of debris. The fact that 2025 MN45 is still intact, still whole, still spinning at that insane velocity, means that either our models of asteroid composition are fundamentally wrong, or this particular object is made of something far more cohesive and solid than standard asteroid models predict. It would need a cohesive strength similar to that of solid rock. Scientists describe this discovery as somewhat surprising, which, in the careful language of academic astrophysics, is roughly equivalent to saying their jaws hit the floor. And this is where everything changes, because the significance of 2025 MN45 is not just about one weird spinning rock. It is about what the discovery implies for the broader population of asteroids in our solar system. If Rubin found 19 superfast rotators in its very first months of looking, in a small patch of sky during a test phase, then the question becomes, how many more are out there? How many more objects exist in the asteroid belt and beyond that violate our existing physical models? How many more things are doing things that they are not supposed to be able to do, hiding in the dark between planets, waiting to be seen? Once fully operational, Rubin is expected to detect thousands of new asteroids every week. About 90% of potentially hazardous asteroids larger than 140 meters that could approach Earth within 7 million kilometers every week. Not every year, every week. The scale of what this telescope is going to find is genuinely difficult to comprehend, and it could also find over 50 interstellar objects, objects that did not form in our solar system at all. Rocks and comets that originated around other stars were flung into interstellar space by gravitational interactions with their home systems, drifted through the void between stars for millions or billions of years, and are now passing through our cosmic neighborhood as alien visitors from another stellar system entirely. We have found 2 such objects in all of human history. Currently, only 2 such interstellar visitors have been discovered. 1I Oumuamua and Comet 2I Borisov. Oumuamua, discovered in 2017, was so strange in its behavior and shape that it still has not been fully explained to the satisfaction of the scientific community. Its acceleration as it moved away from the sun was anomalous. Its shape was unlike any known comet or asteroid. Some scientists proposed it might be a piece of alien technology. Others offered more conventional but still exotic explanations involving hydrogen ice or solar radiation pressure. The debate is still ongoing. Borisov, found in 2019, was more conventionally comet-like, but still represented only the second interstellar object ever identified. 2 objects in the entire span of recorded astronomical history. And the Vera Rubin Observatory, over the next decade, is expected to find more than 50 interstellar visitors, 50 objects from other star systems. And when that happens, when we hold in our hands real data about the composition and behavior and origins of those objects, we will know more about the planetary systems of other stars than we ever thought possible. We may know, for the first time, whether the building blocks of life that exist on Earth also exist out there, carried through the galaxy on the backs of interstellar wanderers. But let's pull back for a moment and look at the larger picture, because the asteroids and the interstellar objects, as extraordinary as they are, represent only one corner of what the Vera Rubin Observatory is actually designed to do. The real mission, the 10-year campaign that officially launched on June 30th, 2026, is called the Legacy Survey of Space and Time, the LSST, and the ambition behind it is almost beyond articulation. The Vera Rubin Observatory is now capturing the cosmos in unprecedented detail, transforming the way we study the dynamic universe. From a mountaintop in Chile, under clear, dark skies. Rubin Observatory has begun the revolutionary legacy survey of space and time, the 10-year survey that is Rubin's signature campaign to create the most comprehensive cinematic record of the universe in history. The word cinematic is intentional. What Rubin is doing is not simply taking photographs of the sky. It is creating a time-lapse film of the entire universe. Every few nights, it photographs the same patches of sky again and again and again, building up a moving record of change, stars that flicker, galaxies that shift, objects that appear and then vanish, transient events, explosions, collisions, the deaths of stars, the births of black holes, captured in real time, flagged automatically, and broadcast to observatories around the world within 60 seconds of detection. Rubin tested out its alert system for the first time on February 24, 2026. By photographing a patch of sky for which previous surveys had already built up a sufficient template, Rubin was able to ping 800,000 alerts in a single night. Everything that changed, appeared, or disappeared was cataloged and triggered an alert, said Stephen Smart of the University of Oxford. 800,000 alerts in one night from a single patch of sky. When the full survey is running, scanning the entire southern sky every few nights, that number will become millions. The LSST will unleash a nightly 7 million alert sky survey powered by SLAC's 60-second alert pipeline. 7 million alerts per night, 7 million detected changes in the observable universe every single night for 10 years. The data generated will be so enormous that no human team could sift through it manually. Computer algorithms will sift through the large volumes of data, helping researchers flag any patterns or rare events in a particular patch of sky over time. Artificial intelligence systems will be the first eyes on the data. They will decide what is interesting. They will prioritize the alerts. They will direct the attention of human scientists toward the things that deserve immediate investigation. This is not a small thing. This is a fundamental shift in how science is done. For the first time in history, the machines will be doing the first pass on cosmic discovery. And what they find will be relayed to observatories across the planet, ground-based telescopes, space telescopes, radio arrays, X-ray observatories, all working in coordination, all responding in real time to what Rubin sees. The color-rich images of exploding stars, black holes, and cosmic collisions will also help direct the attention of other observatories around the world, according to a news release, allowing various institutions to work in tandem to collect holistic observations of notable celestial events. Think about the Virgo cluster images that were released with Rubin's first light data. The Virgo cluster images show the chaotic jumble of merging galaxies, a process that plays a crucial role in galaxy evolution. The level of detail, from the large-scale merging galaxies to details in the spiral structure of individual galaxies, more distant galaxies in the background, foreground Milky Way stars, all in one image, is transformative. In a single frame, Rubin captured not just one galaxy, but an entire ecosystem of galaxies, nearby and distant, foreground stars from our own Milky Way, mixed in with structures billions of light years away. The camera, seen here mounted to the telescope, weighs about 3,000 kilograms. You would need hundreds of ultra-high-definition TV screens to display just one of its images. Hundreds of screens. Every single image Rubin takes is a world unto itself, containing more information than most telescopes could capture in months of observation. Now here is where the story turns from extraordinary to genuinely, deeply unsettling. Because all of that, the asteroids, the interstellar objects, the merging galaxies, the time-lapse of the cosmos, all of that is the prologue, the opening chapter. The real question, the question that drives the entire 10-year mission at its core, is the one about the 95% of the universe that we cannot see and do not understand. The LSST will produce the first high-precision independent test of whether dark energy is a fixed cosmological constant or has evolved over the history of the universe, and recent results continue to show hints that dark energy may not be a fixed cosmological constant, but something that has evolved. Let's pause on that for a moment, because it is genuinely one of the most consequential sentences in modern cosmology. Dark energy is the name scientists give to whatever is causing the expansion of the universe to accelerate. In 1998, astronomers discovered, to widespread shock, that the universe is not just expanding, but expanding faster and faster over time, as if something is pushing everything apart at an ever-increasing rate. They called this thing dark energy, and they slotted it into their equations as a cosmological constant, a fixed background property of space itself. That was the tidy explanation. Dark energy exists. It is constant. It has always been the same strength, and it always will be. But what if it isn't constant? What if dark energy changes over time? What if it is not a fixed property of space, but something more dynamic, something that has evolved over the 13.8 billion year history of the universe, something that could continue to change in the future? This is not a theoretical curiosity. If dark energy is not constant, if it can change, then the ultimate fate of the universe becomes radically uncertain. Our models of how the cosmos ends, of how long galaxies can survive, of whether structure in the universe will continue to form or will be torn apart, all of those models depend critically on the behavior of dark energy. And according to data from multiple independent observatories, there are growing hints that it may be evolving. Not confirmed yet, not proven. But the hints are real, and they are persistent, and they will not go away. After a full year of data from LSST, these measurements are expected to reach precision comparable to recent dark energy spectroscopic instrument results, providing an independent test of hints that dark energy may evolve over time. What most people are not seeing is the full weight of what that means. Because if dark energy is evolving, then the physics that governs the structure of reality at the largest scales is more complicated than our best current theories can explain. It means that Einstein's cosmological constant is not the final word. It means that general relativity, our most successful theory of gravity, may need to be extended or modified. It means that the 95% of the universe we don't understand may be behaving in ways we haven't even begun to model correctly. And the Vera Rubin Observatory, over the next decade, is going to give us the data to test all of this. It is going to measure the shapes and positions and movements of billions of galaxies with such extraordinary precision that we will be able to map the distribution of dark matter across the observable universe with a clarity never before achieved. LSST will probe dark matter through a wide suite of observations, including measurements of Milky Way satellites, stellar streams, galaxy clusters, weak lensing, microlensing searches for primordial black holes, and studies of stellar populations and stellar remnants. This is what scientists call weak gravitational lensing, the subtle bending of light from distant galaxies as it passes through the invisible web of dark matter that permeates the cosmos. By measuring those tiny distortions across billions of galaxies, Rubin will map the dark matter scaffolding of the universe in 3 dimensions, tracing the invisible architecture on which all visible structure is built. That dark matter web, the cosmic skeleton that holds galaxies together, that guided the formation of every star and planet in the universe, that is somehow connected to the woman whose name this telescope bears, is what Vera Rubin herself discovered the evidence for in the 1970s. The observatory is named after astronomer Vera Rubin, who provided the first convincing evidence for the existence of dark matter. She was studying the rotation curves of galaxies, measuring how fast stars orbited around the galactic center, and she found something that did not make sense. Stars at the outer edges of galaxies were moving far too fast. By all rights, given the amount of visible matter in those galaxies, those outer stars should be moving slowly, like the outer planets of our solar system move more slowly than the inner ones. But they weren't. They were zipping around at speeds that implied the presence of enormous quantities of unseen mass, dark matter, distributed in a halo around every galaxy she measured. She spent years fighting to be taken seriously. The establishment resisted, but the data was undeniable, and eventually the scientific community accepted what she had found. The universe is full of invisible matter that we cannot detect directly, cannot see with any telescope, cannot touch or measure except through its gravitational effects on everything around it. Vera Rubin gave us the problem. The telescope bearing her name is designed to help us solve it. NSF-DOE. Rubin Observatory will capture more information about our universe than all optical telescopes throughout history combined. All of them. Every telescope ever built by human civilization. From Galileo's first crude instrument to the Hubble Space Telescope to the most advanced ground-based observatories of the modern era. All of that combined data will be exceeded by what Rubin captures in its 10-year survey. When the LSST is complete, the final dataset will contain billions of objects with trillions of measurements, all accessible through regular data releases. This is the first time so much astronomical data will be available to so many people, opening the door to new kinds of discoveries by both scientists and the public. The public, not just professional astronomers, not just PhDs working at elite institutions. Anyone who wants to look at the data will be able to access it, explore it, analyze it. Amateur astronomers and curious students and data scientists and AI researchers will all be able to participate in the exploration of the cosmos in a way that has never been possible before. This is not just a scientific instrument, it is a democratization of the universe. But let's come back to the timeline, because the pace at which this observatory has moved from first light to full operations is remarkable and worth understanding in detail. The Vera C. Rubin Observatory achieved its first photon with the LSST camera on April 15, 2025. That was the moment the camera first opened its eye and saw the universe. From that first photon to the full public release of first light, imagery took just 2 months. The first images, released by the Vera Rubin Observatory, were stunning in their resolution, combining 668 separate images taken in just over 7 hours of observing time, clearly revealing otherwise faint or invisible details, such as the clouds of gas and dust that comprise the Trifid Nebula and the Lagoon Nebula, which are several thousand light years away from Earth. 678 images stacked together to reveal clouds of cosmic gas and dust in unprecedented detail. And that was in just over 7 hours of observation during a test phase. Then came the optimization surveys, during which the asteroid discoveries mounted. Then came the alert system test in February 2026 that produced 800,000 alerts in a single night. Then came April 2026 and the announcement of 11,000 discovered asteroids. And then, on June 30th, 2026, the real mission began. On June 30th, 2026, the NSF-DOE Vera Rubin Observatory atop Cerro Pachon in northern Chile officially started the Legacy Survey of Space and Time, a decade-long publicly funded effort to photograph every corner of the southern sky hundreds of times over, generating the most comprehensive record of the universe's changing face ever assembled. The announcement came simultaneously from NSF Noir Lab, DOE's SLAC National Accelerator Laboratory, and from ELAB, marking the formal end of a 25-year construction and commissioning arc, and the beginning of what the observatory's leadership is calling a new era in astrophysics. Today we begin filming the greatest cosmic movie ever made. That was the statement from the NSF director on the day the survey launched. Not a metaphor, a precise description of what this machine is doing. It is filming the universe, frame by frame, night by night, year by year, building a record of cosmic change that will outlast every scientist alive today. The data Rubin collects will be studied by researchers for generations. Discoveries made from the LSST dataset will be announced not just in the next decade, but in the decades that follow, as astronomers dig deeper into the archives and find things that nobody noticed the first time through. And here is where the story becomes genuinely open-ended in ways that should make you feel something. Because the Vera Rubin Observatory is not just going to find what scientists predicted it would find. NSF-DOE. Rubin Observatory will find things that no one even knew to look for, according to an NSF program director for research infrastructure. When Rubin's Legacy Survey of Space and Time begins, this huge spinning asteroid will be joined by an avalanche of new information about our universe, captured nightly. Things that no one knew to look for. This is the honest admission at the heart of modern astronomy. The universe is almost certainly stranger than our best theories predict. There are almost certainly phenomena out there that do not fit neatly into any existing model, that will require entirely new frameworks to explain. The history of astronomy is a history of exactly these kinds of surprises. Pulsars, quasars, gamma-ray bursts, gravitational waves, fast radio bursts, all discovered when a new instrument pointed at the sky in a new way and saw something that nobody was expecting. Rubin will do this. It is designed to do this. The combination of its field of view, its cadence, its sensitivity, and its alert system means that it will catch transient events, things that happen quickly and then are gone, that every previous telescope in history would have missed entirely because it wasn't looking at the right patch of sky at the right moment. Rubin will take images of the entire night sky over the southern hemisphere once every few days for a decade, creating the world's largest time-lapse. Every few days, the entire southern sky, for 10 years. There's nowhere left to hide for the transient universe. Supernova explosions, neutron star mergers, black hole accretion flares, gamma-ray burst afterglows, gravitational wave counterparts, all of it will be caught, cataloged, and broadcast to a global network of responsive observatories within 60 seconds. What most people are not seeing is that we are living in the single most extraordinary moment in the history of observational astronomy. The James Webb Space Telescope, launched in 2021, is showing us the universe at infrared wavelengths with unprecedented sensitivity, peering back to within a few 100 million years of the bigs. Bang, and revealing the first galaxies with a clarity that continues to challenge theoretical models of early cosmic structure. And now Rubin, on the ground in Chile, is performing a completely different but equally revolutionary function, not peering deep and narrow like Webb, but scanning wide and relentlessly, building the cosmic time-lapse that Webb cannot provide. These two instruments are complementary in their vision of the universe, and together they represent the most powerful 1-2 punch in the history of space science. The real story is that we are at the beginning of an age that will fundamentally rewrite our understanding of what the universe is and what we are doing in it. The questions Rubin will address over the next 10 years are not peripheral or esoteric. They are foundational. What is dark matter? What is dark energy? Is the cosmological constant actually constant, or has it been changing throughout the history of the universe? Are there other objects passing through our solar system right now that originated around other stars? And if so, what do they tell us about whether life's chemical ingredients are distributed throughout the galaxy? Are there asteroids on collision courses with Earth that we have not yet identified? During the next decade, LSST will be able to confirm or dispute if tensions seen today in cosmological data are due to new physics. New and unexpected phenomena could confirm or disrupt our current understanding of the universe. Confirm or disrupt, those are the two options on the table. Either the data Rubin collects over the next decade confirms our existing models of cosmology, filling in the details and tightening the parameters, or it disrupts those models entirely, revealing that our understanding of dark matter, dark energy, and the fundamental physics of the universe is incomplete in ways we have not yet imagined. Both outcomes are scientifically revolutionary. The confirmation would be a triumph of human theoretical understanding. The disruption would launch a new era of physics, forcing the construction of new theories to explain a universe stranger than the one we thought we were living in. The result will be an ultra-wide, ultra-high-definition time-lapse record of the universe. It will bring the sky to life with a treasure trove of billions of scientific discoveries. Billions. Not thousands, not millions, billions. Each one a piece of the puzzle, each one a window into some corner of the cosmos that has never been seen before in human history. Consider what it means that a camera on a mountaintop in Chile is about to generate more knowledge about the universe than all previous generations of astronomers combined could gather in their lifetimes. Consider what it means that the 95% of the universe we don't understand is finally being systematically interrogated by an instrument powerful enough to leave a mark on that ignorance. Consider what it means that right now, tonight, as you go about your life, that eye on the mountain is open, sweeping the southern sky, catching photons that have traveled for billions of years through the expanding fabric of space-time to land on the largest camera humanity has ever built. The universe has been keeping secrets for 13.8 billion years, and we just built something powerful enough to start making it talk. But here's the question that nobody can answer yet. Here's the thing that should keep you awake at night in the best possible way. What happens when Rubin finds something it wasn't looking for? What happens when the algorithms that process 7 million alerts a night flag something that doesn't fit any known category, something that is not an asteroid, not a supernova, not a galaxy, not a known transient phenomenon, but something else entirely? What happens when the greatest observational instrument in human history points at the universe and the universe points something back? We don't know. We genuinely do not know what this telescope is going to find over the next 10 years. We know what we are hoping to find. We know what our models predict we will find. But history has a way of making those predictions look modest in retrospect. Every time humanity has built a significantly more powerful instrument and turned it on the sky has returned something unexpected, something that didn't fit, something that required us to fundamentally revise our picture of reality. The first images shown to the public provide just a taste of Rubin's discovery power. Just a taste. The full meal is a decade long, and it has only just begun. The 11,000 asteroids we didn't know about until a few months ago are just the opening paragraph of a book that nobody has read yet. The 33 near-Earth objects are a reminder that our solar system is not the well-mapped, well-understood neighborhood we assumed it was. The superfast rotating asteroid 2025 MN45 spinning every 1.88 minutes is a physical object defying our models, sitting in the asteroid belt between Mars and Jupiter, reminding us that we do not fully understand even the rocks closest to home. And beyond the rocks, beyond the asteroids and the comets and the interstellar visitors, lies the deeper mystery, the 95%, the dark architecture of the cosmos, the invisible scaffolding on which everything we have ever seen is built, the expanding force that is pushing the universe apart at an accelerating rate toward a fate we cannot yet calculate with confidence. The Vera Rubin Observatory is now fully operational. The greatest cosmic movie ever made has begun filming. The data is flowing in at 20 terabytes a night. The algorithms are running. The alert system is live. The world's astronomical community is watching, waiting, ready to respond. And somewhere in that data stream, in the flood of photons from a billion galaxies, in the light curves of 1 million transient events, in the orbital mechanics of 100,000 newly discovered asteroids, somewhere in all of that, there is probably an answer to at least one of the questions that have kept cosmologists awake for decades, and possibly something far stranger than any of the answers they were expecting. The eye never blinks, and what it is about to show us may change everything.